Hello. The purpose of this video is to show you how to use different ground positions and how the solution of an electric problem will change when you pick different ground. Okay, so here I choose that problem. It's a very simple problem. We have one independent current source, one dependent current source, and we would like to find the V output here using nodal analysis. This is really the target of this problem. So the classical way or the straightforward approach that we got used to in classes is simply we select this bottom node here to be ground. Okay, so in general we have one node, second node, third node, and the fourth node. Notice that this one and this one here are the same node. Okay, this one here are the same node, so I don't have to say a fifth node, just 1, 2, 3, and 4. We're going to take node number 4 as ground, and then we start to solve the problem using nodal analysis for the nodal voltages relative to ground. So we will have to get three equations to solve for the nodal voltage here, here, and here. Okay, so I labeled the nodes this way. This is node 1, node 2, node 3, and I took node 4 as ground. So I don't have to write an equation at node 4 because I know that the voltage here is 0. I gave it the value 0. As we agreed in classes, there is nothing called absolute voltage. It's only relative voltage. So now when I say V1, I mean V1 relative to ground, V2 relative to ground, V3 relative to ground. Okay, these are the things we're solving for. Let's write KCL at node number 1. As we agreed in classes, we say the sum of all currents leaving that node equal to 0. So Vx over 4000 plus V1 minus V2 over 2K minus 1 milliampere is equal to 0. This is the first equation here. After this equation, whether in loop analysis, nodal analysis, you have to get rid of the controlling parameter Vx. This is Vx here, and Vx, as you could see, is nothing but V2, because V2 relative to ground is the voltage of this point relative to ground is the same as Vx. So I replace Vx by V2, I multiply both sides by 4k, and I collect the coefficients. I end up with this equation between the three unknowns V1, V2, and V3. V3 is not there, but as we agreed in class, we have always to keep these unknowns in order, and whenever I have a missing coefficient, I put it with 0. Okay, this will help me later when I enter the matrix into my calculator, or when I want to even do it using elimination or whatever. Okay, let's apply KCL at node number 2. This node number 2, sum of all currents leaving this node are equal to 0. V2 minus V1 over 2K, V2 over 3K, V2 minus V3 over 1K is equal to 0. I have these three currents. I multiply both sides by 6K, and I collect the coefficients. I end up with this one here. I'm not showing all the intermediate simplifications. I did them in an external piece of paper. I just don't want to cram that's this slide here, but I encourage you to take a minute and to try to see that what I did was multiply 6K, and then I collected all the coefficients of V1, V2, and V3. Okay, we have one more node, node 3, to write KCL at. So we can say the sum of all currents leaving this node equal to 0. So V3 minus V2 over 1K minus Vx over 4000 plus V3 over 3K is equal to 0. So I have this current, I have this current, I have this current. And because this one is flowing in, I include it with a negative sign. So we have these three currents. Get rid of Vx as we did before. Write Vx as V2. Okay. They have here 3K, 1K, 1K. Multiply both sides by 12K and collect the different coefficients. You will end up with this equation. Please verify this yourself. Pause the video. Verify that this equation you're going to be getting. I did this in detail in an external piece of paper, but I'm not showing it here. Okay. Now I have three equations, three unknowns. I can solve them. I used MATLAB to get the solution, and this is the solution I ended up having. 2.7742, 1.4484, and this one here is for V3. Okay, so what do these numbers mean? These are the voltages of the node 1, 2, and 3 relative to node 4. But we took node 4 to be ground. We took it to be 0. So if you want to draw a diagram, this is what's happening. All the solutions we got are positive. So this is V4, it is 0 volts. This is V3 is higher than V4 by 1.4516. V2 is higher than V4 by 1.5484. V1 is higher than V4 by 2.7742 volts. So this means this explains the solution. The numbers we got here, the three numbers we got here, are the relative voltages of these three nodes relative to ground. Okay, so now we're gonna repeat the problem again, but we're gonna take a different ground and see how the solution is going to change. So now I took node number 2 to be ground. Okay, so I took this to be ground. So now I have three unknowns, V1, V3, and V4. V4 is not ground anymore. And when I say V1, I mean V1 relative to node 2, V3 relative to node 2, V4 relative to node 2, which is now ground. Okay? Again, we have three unknowns, and I need three equations. And as we agreed in nodal analysis, we apply KCL. This problem does not have any voltage sources, so it's a little bit easier to handle. I baked it that way to focus on the concept of different ground only. So let's write KCL here. Sum of all currents leaving node 1 is equal to 0. So minus 1 milliampere plus V1 over 2K. You can see that this, I'm not saying V1 minus V2 anymore. V1 over 2K plus Vx over 4K is equal to 0. Okay. What is Vx? Vx is the voltage difference between this point and this point. But this is ground and this is node 4. Then Vx is minus V4. It's different from last time. The interpretation of Vx different. So you have to go back here, get rid of the controlling parameter, and this is what we have to do in nodal analysis, loop analysis. Every time you see controlling parameter, you remove it and replace it, express in terms of the unknowns. Now, if you get rid of Vx here, multiply both sides by 8k, and you collect all the different coefficients, you end up by this equation governing V1, V3, and V4. Remember, we are solving for V1, V3, and V4. There is no V2. V2 is 0. I know what's V2. Okay, so I write I write them in order: V1, V3, and V4. Let's talk about node number 3. Node number 3 here has again three currents flowing out. This now is V3 over 1k. This one is minus Vx over 4k. This one here is V3 minus V4 over 3k. Okay, this is not ground anymore. Okay, so these are the three currents. I'm gonna replace Vx by minus V4, multiply both sides by 12k, and collect similar coefficients. You obtain this equation here. This is my second equation. Okay, so I need one more equation. I have to get it from writing KCL at node number 4 here. So we go to node number 4, we write KCL. Sum of all three currents flowing out from this node is equal to 0. So 1 milliamp is flowing out plus V4 over 3k plus V4 minus V3 over 3k is equal to 0. These are the three currents. Multiply both sides by 3k, collect all similar coefficients, you obtain this equation. Now I have three equations, three unknowns. I solve for them. I used my MATLAB program. You can use your calculator. Your calculator can solve 3 by 3. You must be very fluent in doing this. Okay, you obtain V1, V2, and V3. Notice two of them are negative right now. Okay, two of them are negative. So let's now try to make a diagram showing the different voltages. Okay, what is the interpretation of these numbers that we got? If you draw that diagram, this is what you see. V4 is negative, minus 1.54. V3 is negative, minus 0.0968. V2 is 0, we select to be 0, and V1 is positive. So this diagram is exactly the same diagram that we had before. But before we were using 0 to be here. When 0 is here, and because V3, V2, and V1 were higher than node 4, then all these numbers were positive. But when we selected our reference to be V2, we made this one 0, so only V1 will be positive, and V2 and V3 will be negative. What if I select V1 to be 0? If I go to node number 1 and make it ground, all the three solutions I'm going to be getting will be negative. Okay, so you can see that the relative voltage between one and the other did not change. It's just these absolute numbers that changed because we are now taking different reference. Okay, but the difference between this one and this one, or this one and this one, or this one and this one is still the same. It did not change. And I do encourage you to repeat that same problem again. Take node number 1 as your ground, or take node number 3 as your ground, and see if you take node number 3, you'll see that V1 and V2 will be positive, V4 will be negative, but the relative position of the solution is the same, and you can double check that this exactly the same relative positions we got in the first case. So ground, you can solve the problem using any point as your ground. This is really a reference that you pick. It does not affect the relative voltages. It just affects the readings that you're going to be getting. Okay, relative to ground. So because ground just the one that changes, whether ground is here or here or here or here, but the relative voltages between any one of these 2 points still remain the same. V2 here is higher than V3, V3 is higher than V4, V1 is higher than V2 by the same amount. Okay, so I hope that clarifies the concept of using different grounds in your solution.